Welcome to this explainer. If you're a focused learner looking to take your AI workflows to the absolute next level of accuracy, well, you are in exactly the right place. Today, we're unpacking a fascinating and highly effective technique that's going to fundamentally change how you prompt large language models. We're exploring a concept called universal self-consistency, and I promise you, by the end of this, you are absolutely going to want to implement this into your own projects immediately. So let's get started.
So we all know the common pain points of working with generative AI, right? You ask a complex question, and sometimes the model just, well, it hallucinates. Or maybe it gives you a reasoning path that just doesn't quite make sense. Now, when you're dealing with a math problem where the answer is simply 42, it's a bit easier to check. But how do you make AI reliable when you're dealing with truly open-ended tasks? Think about writing code, or summarizing a massive document, or generating an essay. In these scenarios, there's no single right answer. Finding a way to force the AI to be reliable and consistent when the output is just free-form text, man, that has been a huge challenge.
Okay, let's dive into this and look at how we've traditionally tried to solve this problem versus the new approach. You might already be familiar with standard self-consistency. This is where you basically ask the AI the exact same question multiple times, and then you just tally up the exact matching answers. If 3 out of 5 times the AI says the answer is 7, you assume 7 is correct. Makes sense, right? But that really only works for structured answers, like single values in math or maybe logic puzzles. Universal self-consistency, or USC, is the missing link here. It extends this incredibly powerful idea to free-form responses. So instead of you having to extract identical answers to count votes, USC leverages the AI itself to handle that free-form or structured text, making it absolutely perfect for open-ended Q&A.
So let's formally define this. Universal self-consistency is a prompting technique where a large language model compiles its own multiple generated responses and then selects the most internally consistent answer from among them. And this brilliantly illustrates a very human concept. Think of it kind of like this. Imagine you need to solve a really complex problem. You ask 5 different experts the exact same question. They all go into separate rooms, do their research, and write out a detailed response. Then you bring all 5 of those reports into a boardroom, hand them to a lead expert, and say, hey, read all of these and tell me what the ultimate consensus is. That is exactly what USC is doing, but it's happening entirely within the AI.
The really crucial point here is how incredibly intuitive and actionable this is. You do not need to be a machine learning engineer to use this. It literally boils down to 2 simple steps that anyone can implement in their prompts right now. Step 1, you generate multiple responses using chain of thought prompting. This just means you ask the model your question several times and you ask it to show its work, which ensures you get a good diversity of reasoning. Step 2, you take all of those unique answers, drop them into a new prompt, and simply ask the model to select the most consistent answer. That's really it. Generate, then select.
USC in action. Astronomy. Let's take a look.
Theory is great and all, but let's see how this actually builds in a real-world scenario. We're going to start with our initial prompt. It's a basic question for step 1, which planet in our solar system is the largest? Now, instead of just asking this once and taking the very first thing the AI spits out, we are going to run this exact same prompt 5 separate times to generate a diverse pool of responses. Here we've summarized the 5 different outputs the AI generated. Notice how they all eventually arrive at the exact same correct conclusion, Jupiter, but their chain of thought reasoning is completely different. For example, response 1 just listed the planets in order of size and picked the top one. Response 2 compared their diameters, noting Jupiter's is about 142,000 kilometers. Response 3 stated Jupiter's diameter is 11 times that of Earth. Response 4 used a volume comparison, pointing out that over 1,300 Earths could fit inside Jupiter. And finally, response 5 grouped the planets by inner and outer, comparing their relative sizes sequentially. So we've got 5 very different logical paths.
Now we move right into step 2. We take all 5 of those responses and we paste them into a single new prompt. This is our magic selection prompt. It acts as that lead expert we talked about earlier. We just tell the AI, I have generated the following responses to the question, we list them all out, and then we give the crucial instruction. Evaluate these responses. Select the most consistent response based on majority consensus. Start your answer with, the most consistent response is response X.
Now, what's really interesting to see here is that out of all the varied logic it provided previously, the AI evaluates its own work and outputs the most consistent response is response 4. If you recall, response 4 was the one that provided that fantastic, tangible detail about how over 1,300 Earths could fit inside Jupiter. The LLM successfully reviewed its own committee of answers, synthesized the logic, and identified the most robust,
contextually rich and consistent answer from its own variations. How cool is that?
The proof: benchmark results.
So you might be wondering, is this extra prompting effort and token usage actually worth the time? Let's look at the data. The source outlines 3 distinct areas where this technique absolutely drives. First, mathematical reasoning. Even though we said standard self-consistency works for math, USC maintains at high accuracy without you needing to write custom scripts to extract specific numerical formats. Second, code generation, things like writing Python or SQL. USC selects the code with the most consistent logic among the samples. What's absolutely amazing here is that it matches the accuracy of execution-based voting, which requires actually running the code to see if it works, but USC does it without needing the computational resources to execute the code. And third, summarization and open-ended generation. This is where it evaluates multiple summaries of long documents and finds the one that best captures the consensus of all the drafts.
The hard data really speaks for itself here. Check out this comparison across 4 major benchmarks. For math on the GSM-8K benchmark, USC hits 90.2%, which practically matches standard self-consistency, but with way more flexibility. For code generation on the Arcade benchmark, it hits 30.1%, beating greedy decoding and random selection. But look at the bottom 2 rows. For summarization on the Gov Report benchmark, it scores a Rouge 1 of 40.2. And for Truthful QA, which tests open-ended truthfulness, it scores 67.7%. What you really need to take away here is that for those last 2 tasks, standard self-consistency is labeled not applicable. You literally cannot use standard vote tallying on open-ended summaries or truthful Q&A. USC unlocks consistency and reliability in areas where we previously had no simple way to mathematically enforce it. That's a real game changer.
We've seen the methodology, we've walked through the practical steps, and we've verified the performance data. Universal self-consistency proves that sometimes the best way to get a flawless answer out of an AI is to ask it to brainstorm and then ask it to be its own toughest critic. So, I want to leave you with a provocative thought as we wrap up this explainer. If the AI can now reliably evaluate its own best thoughts, synthesize free-form text, and filter out its own hallucinations without complex external programming, what will you build with its newfound clarity? Take these 2 simple steps, apply them to your next complex prompt, and see the difference for yourself. Keep learning, keep experimenting, and hey, thanks for joining me today.